What I'm showing you here is a shoulder button input system that uses a bridge architecture to communicate between the player controller and the character blueprint. What this system does, it allows you to map gameplay mechanics like lock-on or magic to the controller's shoulder button in a clean, organized way. The first thing I'm going to show you is the trigger enhance input action. Everything begins in the player controller blueprint with an enhance input action. When the lock on button is triggered, it calls a custom called shoulder button input. It passes two pieces of data, a boolean for whether the button is currently pressed, and an input type, like lock on for instance. Inside the player character blueprint function, the system runs a safety check. It utilizes a custom node called getCharacterBlueprint to find the player's avatar. It checks an isAlive boolean. If the character is dead, the logic stops immediately to prevent the player from using abilities while in a game over state. And do keep in mind that this feature is common amongst all action games, even Devil May Cry, Bayonetta, and Metal Gear Rising. Now let's move on to the router. Switch on enum. Once validated, the system uses a switch on shoulder input type. This acts as a traffic controller, routing the signal based on which ability was requested. Projectile magic routes to logic that sets the project magic button state. Log on routes to logic that sets the target logon state. What comes next after that is the bridge, interface communication. This is where the controller talks to the character. After updating the local boolean, the system calls the shoulder button input on the player character. By using an interface message, I'm basically maintaining the decouple architecture earlier. The controller sends the command and the character decides how to execute it. This is the debugger character reception. It shows the receiving end inside the character blueprint. Currently, this logic is used for development only. Whenever the character receives the signal, it prints a string to the screen that converts the enum to string. This allows me to verify in real time that the character is correctly hearing the controller's command. For example, the screen will flash the moment I press the lock-on button. This is where I built a robust pure function system to safely identify and validate the player stats before any combat or movement logic executes. This is a crucial part of my bridge architecture between the player character and the character blueprint. What I have here is getCharacterBlueprint, pure function. This function acts as a safety gate to ensure the player controller is talking to the correct type of character. Interface validation. It takes the current player character and immediately asks, does object implement interface, specifically checking for character BPI, otherwise known as blueprint interface. safety branch. If it is true, it proceeds to communicate with the character. If false, the logic stops, preventing the controller from accidentally trying to launch or damage an object that isn't a valid character. Once validated, it calls isCharacterAlive to get the current health status and returns the character reference as a usable object. Speaking of isCharacterAlive, this is a simple but effective health check located inside the character blueprint. It looks at a float variable named Vitality. It checks if vitality is less than or equal to 0. The not node, because the function as isCharacterAlive, it uses a not node to flip the logic. If the health is less than 0, the check is true, but the not node turns it into false, meaning they are not alive. The reason why this is important is because using these pure functions, I'm making my code much cleaner. I can simply drop these nodes anywhere I need to check the player's status without having to drag a long white execution lines across my entire blueprint. Next, I'm going to show you what's called lock-on toggle and cleanup system inside the character blueprint. This logic handles the transition between being free and being locked onto an enemy, including the visual management of my target reticle, which is located inside tick variables within the event tick. This is what's called the toggle gate, which is the initial check. The process begins by checking if the player has pressed the target button. If the button is pressed, the system checks on the current status of the isLockOn boolean. If I'm already locked on, the system moves to section 4 to clear the target. If I'm not locked on, it proceeds to find a target. When toggling on, the system attempts to find a valid enemy to orbit. It triggers a custom function or interface called setLockOnTarget. Before assigning a target, it checks if the discovered locked target is actually different from the player. This prevents the camera from accidentally locking on to your own character model. If a valid target is found, the system updates the character state. It sets the locked target variable to the new enemy actor. It sets isLockOn to true. When I press the button while already locked, or if the target is lost, the cleanup phase begins. The locked target is cleared, set back to self or null, and isLockOn is set to false. The last part is where I show the UI element is handled during the cleanup phase. To prevent the reticle from floating in space after the enemy is gone, the system uses attach component to component to snap the target reticle back to the player's own capsule component. Finally, it calls setHiddenGame on the target reticle with the new hidden check. This ensures the UI icon disappears the moment the lock-on is deactivated. Simply put, this is a perfect example of a toggle state machine. I'm using the same input button to drive two different logic paths based on a single boolean. This keeps my controls intuitive for player, one button for aim, and the same button for stop aiming, or in this case, hard button press.
This is set lock on target function inside. What I have here is I've created a sophisticated target selection and soft lock on system. It doesn't just pick an enemy, it uses mathematical dot product and distance checks to search for the best target currently in front of my character or camera. This is where the search phase begins, iterating enemies. The logic starts by looping through a list of potential targets called enemies, which I have right here from Get Game Mode. Of course, I made a blueprint interface for it, but I will get to that on the next video. What this does is it ensures the current element is within the loop, not the self. Sorry, that didn't came out right. What I actually meant to say was, what this does is it makes sure the current enemies inside the loop is not the character itself, the player character. It's focused primarily on the enemies. It verifies if there is a significant player input to help determine if the player is trying to steer the lock on toward a specific direction. What you're seeing right here is exactly what I'm talking about here. This here is the directional alignment. It's the core intelligence of my system, calculating the unit direction from the player enemy and using a dot product to compare it with the player's current aiming input direction. This local variable, or called best angle, which is a float variable by the way, keeps track of the best angle variable. Whenever the new enemy in the loop is on the front line, having a higher dot product result than the previous one, it updates the best target. This is where the tiebreaker comes in. Check the distance. If two enemies or more are roughly at the same angle, the system uses distance as secondary filter. It compares distance to the current actor against the shortest distance variable, which is also a local variable. Whenever an actor is closer, it updates the shortest distance, setting the actor as the new potential target. Once the loop completes the best target, When the loop finishes as the best target is identified, the system finalizes the lock-on. Validation, meaning checking if the best target is valid, aka found. It sets the lock target variable and flips the is locked on to true variable, which is the one I have right here. And finally, the visual phase, which is the Reticle part here. This provides visual feedback to the player as it uses attach component to component to snap my target reticle user interface component directly onto the enemy's mesh. What I'm doing here is I'm targeting the spine number 2 socket, which is the one I have here. This ensures the reticle stays centered on the enemy's chest, even as they move or fire up certain animations, like swinging a sword or firing energy blast. Visibility wise, it calls upon set hidden in the game unchecked to make the reticle appear. To put it bluntly, rather than having a simple lock on to the nearest enemy, my entire system prioritizes directional intent. In using the dot product, I allow the player to switch targets by simply pointing toward different enemies before pressing the lock-on button. Now I move on to the camera print. What I'm going to show you here is what's called camera location system, which manages how my camera positionally tracks a target. It works in tandem with the rotation system, in which I will explain on my next segment.
does is it takes a raw distance value and scales it to a normalized alpha value. These are the calculations you see here. As for scaling the speed part, this alpha value is then multiplied by 3.0 and applied to the lock-on interp speed. This means the camera will physically move faster or slower depending on the current distance to the target. The last stage blends these calculations into a single smooth movement command. This uses the lerp to choose the individual target position based on the calculated alpha. This one here prevents the camera from jittering or snapping instantly to the new point, as it uses vector interp2, the camera's current actor location, along with the results from the lerp location. The last part here is smooth coordination. It's applied to the camera actor, making it certain that it follows the enemy with a professional fluid motion. In short, my system is essentially stretching and snapping based on the distance. By using the unrotate vector node, I've made certain that the camera's movement is always relative to the player's view, which is crucial to creating a reliable lock-on system in character action games. The next part here is basically the same as the location one, but instead it's rotation. What I've built is what's called a sophisticated camera lock-on rotation system within this blueprint. It dynamically calculates the rotation required for the camera to stay focused on a lock target while maintaining a specific vertical offset. The starting point here is ensuring that there is a valid character to follow. This ensures whether or not the player character is valid, then cast to my character blueprint to access its specific variables, which is the one you're currently seeing here. What this does is it uses a branch to check the boolean is lock on from the character. If the character is not currently locked on, this specific location logic is bypassed.
Once a target is confirmed, the system calculates the necessary angles, which is, of course, the ones you're seeing right now. What this one does, it takes the location of the camera blueprint itself and the lock target to determine a fine look at rotation. Sorry I confused you for this. What I was actually referring to is these two right here, the player and the lock target. If I confuse you, then it's my responsibility to dispel the confusion there. That's on me. And target here is the newly calculated ideal rotation, which is of course make rotator. As for the interp speed, it's controlled by lock-on interp speed, determining how sticky or fast the camera follows the enemy. Lastly, the result of the interpolation is passed into set actor rotation, finalizing the camera's position for that frame. So this system is a great example of target tracking math. By using map range, clamp, and rotation interp 2, I avoid a rigid robotic feeling camera and instead create a smooth professional grade lock-on experience common in contemporary action adventure games like Devil May Cry or Bayonetta. The last part of the tutorial is what's called a dynamic camera zoom system, which is located within the camera blueprint right here. The blueprint in which I'm currently using. What this does is it works alongside my lock-on rotation and location logic to automatically adjust the target arm length based on the camera's angle relative to the ground. The process starts off by validating the player's state. The logic casts to the character blueprint to access the is lock on boolean. If the character is lock on, the system gathers the world locations of the follow camera along with the player character. This part right here determines the steepness of the camera's view. It calculates the normalized direction vector from the camera to the player. By unrotating this direction against the camera's world rotation, it translates world coordinates into local relative space. This multiplier of 2.0 is applied to the z-axis, likely to emphasize vertical changes within the zoom calculation. This is what's called the dot product comparison. It uses a dot product to evaluate the alignment between the camera's local direction and a consistent forward vector. This calculation effectively measures the angle of the camera. The result is subtracted from 1, meaning the zoom effect will intensify as the angle deviates from a direct forward view. logic now calculates the new ideal distance for the camera boom. The angular result is multiplied by a larger factor, which is 2,500, to determine the maximum possible distance variation. The value is added to the default arm length to make sure the camera never pulls in closer than its standard starting distance. And finally, the system applies the change smoothly over time to prevent jarring snaps. The float interpret 2 node compares the current target arm length against the newly calculated target. It uses delta seconds and my lock on interp speed variable to define how quickly the zoom adjusts. The resulting value is used to set the target arm length on the camera boom component. In short, this is what's called a high fidelity combat camera feature. It makes sure that when the player is locked onto a tall enemy, forcing the camera to look up, or when the target moves far away, the camera automatically pulls back to maintain a clear view of both participants and the surrounding environment. Alright, now that that's taken care of, let's test it out and see if it works. That's basically Before I end this tutorial, just in case if you want to know how I change lock on targets, is this one I'm looking for on how to change targets when locking on. Click. Simply put, changing lock targets only works if my player character is alive and I am locking on to a specific enemy. If the player dies, this itself will not work. And I don't think I have to let's test it out again. And there you have it. So that's all you need to know in setting up a lock-on system for your player character. If you enjoyed this video, please like and subscribe to my channel for future tutorials regarding ink stylus action and game creation with the use of Unreal Engine. And do keep in mind that what you take and learn from me is yours to do with as you see fit. Peace out, and I will see you guys on the next video.